course on aircraft propulsion systems. And all we have know already is already at the end of the semester. We are on chapter number 8, propulsion system characteristics. So today we are going to look into the chapter on propulsion system characteristics. We have around 7 subtopics, but for today we are only going to cover the first 3. And we are going to look at the overview, the thrust and efficiency, the trade-off, as well as the reciprocating engine propeller combination. Okay, and our final lecture, lecture 15, we will look at the remaining subtopics. In terms of the introduction, so thrust and the wind is produced are the subject for this particular chapter, and this chapter emphasizes only those aspects of flight propulsion that are necessary for our subsequent discussions of airplane performance as well as design. So we will just only focus on the propulsion aspect of airplane. We will examine in turn the following types of aircraft propulsion mechanisms, including the reciprocating engine or propeller, the turbojet, turbofan, as well as the turboprop. So in each case, we are primarily concerned with 2 characteristics. First one is the thrust. We will look into the thrust, or known as the power, as well as the fuel consumption, right? So these are the 2 propulsion quantities or characteristics that directly dictate the performance of an airplane. Also, note that missing from the above list is the rocket engine. So we will not look into the rocket engine aspect in this particular course, but just to note here, the use of rockets as the primary propulsion mechanism for airplane is very specialized. There are cases rocket also being embedded on airplanes, such as on the Bell X-1, and the first airplane to fly faster than the speed of sound, and the North American X-15, the experimental aircraft. Okay, X-15, the first airplane to fly at the hypersonic speed. Examples of aircraft powered by the rocket engine. But we are not going to look into this kind of applications. We will just focus on the propeller, the turbojet, turbofan, as well as the turboprop. So, looking at the aspect of rockets, rockets are also sometimes used for assisted takeoff, jet assisted takeoff, or known as JATO, which is an acronym for the jet assisted takeoff. It is a bundle of small rockets mounted externally to the airplane. This is been used in World War II as a means of shortening the takeoff distance. For some aircraft, some aeroplanes, they put up a small rocket to provide extra thrust. Okay, why do different aircraft propulsion devices exist? And we know already in the family of turbojet, so we have a turbofan, we have turboprop. Okay, and why do we need such different types of propulsion devices? We have already listed 4 different devices, ranging from the propellers connected to the reciprocating engines or gas turbines to pure turbojet engine. Okay, of course, there is an historical chronological track which we have already covered earlier for each type of the gas turbine engine family. So beginning with the Langley's aerodrome and the Wright Flyer, the first airplane were driven by propellers connected to internal combustion reciprocating engine. Then the invention of the jet engine in the late 1930s, which revolutionized the aeronautics and allow the development of transonic and supersonic aircraft. Because aircraft need to fly further, not just within the region. Okay, so this historical threat is not the answer to the question that I have asked earlier. Why we have such a family of gas turbine engines? For example, many airplanes today are still powered by the classical propeller or reciprocating engine combination. Right? It's already more than 50 years after the jet revolution. Okay, and still why? There is a rather general sweeping answer to this question, having to do with the compromise between having thrust. Is it that we need a very high thrust, or medium thrust, or low thrust? And how about the efficiency? Is it very efficient, high efficient, or medium efficient, or less efficient type of engine? So this is a compromise between the two, between the thrust and efficient. So whether you need a high thrust, low efficiency, or high thrust, high efficiency type of engine. This will be covered in our following section today. Right, so as mentioned, we are going to look into the thrust and efficiency, the trade-off between the two, right? And we shall discuss it now. So in an elementary fashion, we can state that a propeller or reciprocating engine combination which produces comparably low thrust. Of course, as a propeller type of aircraft, the engine, you only need low thrust, but having better efficiency, great efficiency. However, for a turbojet, which considerably higher thrust with less efficiency, and of course, the rocket engine thrust, which produces a huge amount of thrust or tremendous thrust with very poor efficiency. Okay, so in this sense, there is a trade-off. More thrust means less efficiency in this particular scenario. So this trade-off is the reason why all four propulsion mechanisms listed earlier in section 8.1. And the question that we asked, why do we need such a different type of propulsion engine? Okay? So the choice of a proper power plant for an airplane depends on what you want that airplane to do. Whether you want to have a very high thrust, okay, or you want to have a very low thrust, or you want a great efficiency type of engine or poor efficiency type of engine. Alright? So what is the technical reason for this trade-off between the thrust versus the efficiency? Okay, what are the physical reason behind it? At first, let us consider the fundamental way thrust is produced. If we consider this particular figure, a reaction principle in propulsion, which shows a stream tube of air flowing from the left to the right. The free stream velocity, V infinity. We will use V infinity a lot in this subject today, and Vj represents the jet velocity. Okay, so take note that Vj is the jet velocity coming out from the propulsive device. Okay, so this device may be a propeller, it can be a jet engine or turbofan, turboprop is just a generic propulsive device. So the function of the propulsive device is of course to produce thrust, T, thrust to push the vehicle or the aircraft to the left in this particular figure, right, which acting opposite to the drag of the aircraft. Okay, so which being shown in this particular figure 8.1b, showing propulsive device produces thrust T acting to the left. Alright, so no matter what type of propulsive device is used, the thrust is exerted on the device by the net resultant of the pressure and the shear stress distributions acting on the exposed surface areas, internal or external, at each point where the air contact any part of the device. So it will produce a thrust pushing the vehicle to the left in this particular picture. So the pressure and the shear stress distribution are the two hands of nature that reach out and grab hold of any object immersed in the airflow. So these two hands of nature will grab the propulsion device and exert a force on it, namely the thrust as shown here. Okay? So the air which exerts on the device, okay, the air exerts on the device, however, from Newton's third law, namely that for every action there will be an equal and opposite reaction. This is an equal and opposite reaction to the right. So the force will push the vehicle to the left, but there will be an opposite force to the right. Okay? So now imagine that you are the air, okay, where you experience the force T acting to the right, and you will accelerate towards the right if your initial velocity is v infinity, okay, far ahead of the propulsion device. You have a larger velocity of vj downstream of the device as shown here. Okay, we call it as the jet velocity, right? The change in vj minus v infinity is related to the Newton's second law, and we state that the force on an object is equal to the time rate of change of momentum, mv, mass times the velocity. And here the object is the air flowing through the propulsion device, the air flowing through here from left to the right, okay, and the force on the air is given as the T, right? So momentum is the mass times velocity, m dot, the mass flow. For example, the unit will be kilograms per second or slug per second to the free stream tube in this particular case, and we are assuming steady flow, so that m dot is the same across any cross section in this stream tube. M dot is m dot here, m1 will be m dot at exit over here. So the value is the same. Okay. Hence, the momentum per unit time entering the stream tube at the left, which is m dot v free stream, v infinity, and leaving the stream tube to the right as m dot vj, jet velocity. And that's the time rate of change of momentum of the air flowing through the propulsion device is simply the flight momentum flowing out to the right minus the momentum flowing in at the left, namely mvj minus m dot v infinity, or m dot times the difference between vj and v infinity. Okay? So from Newton's second law, this time rate of change of momentum is equal to the force T, the thrust, right? So this will be our equation number 1, and which is the thrust equation for our generic propulsion device. And note that a more detailed derivation of the thrust equation considers the additional force exerted by the pressure acting on the walls of the stream tube. In this particular case, we assume this effect to be very small. Normally, for a complete jet engine equation, you have the element of the pressure times the area of the nozzle. But in this particular case, we assume that it will be very small. Alright? So let us now consider that the matter of efficiency. Okay, between thrust and efficiency just now, which has a lot to do with the wasted kinetic energy left in the exhaust jet. What's coming out here? Okay, what is the kinetic energy coming out at the jet here? So in figure 8.1, we have visualized the situation when the propulsive device is stationary, the air is moving through the device with an initial upstream air velocity v infinity in this case, right? Clearly, velocities v free stream and jet velocity are relative to the device. So if we are sitting in the laboratory with a stationary device, we will see the air moving both in front of and behind the device with velocity of v free stream and vj respectively. Coming from the left, coming out to the right as vj. Right? However, consider the equivalent situation where the propulsive device is moving. Earlier, it is stationary, right? So air coming into the engine being stream and coming out from the jet, the nozzle VJ. But this time, you want to consider the propulsive device or the aircraft is moving with a velocity of v infinity into stationary X, right? So, which is shown in this figure 8.2, the device moving into a stationary air v naught, v equal to 0, right? And this is the usual case in practice because the propulsive device is mounted on the aeroplane, and the aeroplane flies with a velocity of v into the still air. Okay, relative to the device, the flow picture is identical to the sketch 8.1 earlier, with an upstream velocity relative to the device equal to v infinity, and a downstream velocity relative to the device equal to vj. However, for us sitting in the laboratory, we do not see velocities v infinity and vj at all. Rather, we see stationary air in front of the device, we see the device hurtling by us at velocity v infinity. And we see the air behind the device moving in the opposite direction with a velocity negative to the laboratory because you are stationary, okay, at velocity of vj minus v infinity. In this essence, before the moving device enters the laboratory, the air in the room is stationary. So there will be no kinetic energy in the beginning, right? After the device flies through the laboratory, through the room where you sit, the air in the laboratory will no longer stationary. Okay, because the device already flies and you feel some movement of air, okay, which is moving in the opposite direction with the velocity of vj minus v. So this moving air, the vehicle is moving to the left, but you are going to feel the air coming to the right, which is left behind after the device has passed through the laboratory as the kinetic energy. This is what we call it the kinetic energy per unit mass. Okay, we have half times the difference between the velocities vj minus v infinity to the square, right? So this kinetic energy is totally wasted because it performs no useful service to the vehicle itself. It is simply a loss mechanism associated with the generation of thrust. Like a moving aircraft, you are standing still, you experience the air when the vehicle passes through you, you feel the air moving. That is the wasted kinetic energy. And so this is a source of inefficiency. Alright? So we can now define a propulsive efficiency as follows. And we call from the basic mechanics that when you exert a force on the body moving at some velocity, the power generated by that force, power equal to the force times velocity. This will be your equation number 2, and considering an airplane moving with velocity v infinity being driven by a propulsion device with thrust T. So the useful power, called the power available, PA, provided by the propulsive device. So PA is equal to the thrust times the free stream velocity. This will be your equation number 3. So however, the propulsive device is putting out more power than that given by equation 3. Okay, because the device is also producing, remember, the wasted kinetic energy in the air left behind. Right? Because an example that I gave earlier, when the vehicle moves, you feel the wasted energy, the kinetic energy being left. This is meaning that the propulsive device putting out more power than this. Okay, the power is energy per unit time. Okay, the wasted kinetic energy per unit mass of air is half Vj minus V infinity squared as already described above. Okay, so since the mass flow rate m dot of air through the propulsive device mass per unit time, then the half m dot times the velocity difference between Vj and the infinity to the square is the power wasted in the air jet behind the device. Hence, total power generated by the propulsive device is actually equal to the thrust times the free stream velocity plus the mass flow rate. Okay, this is the element of the half m dot times the Vj minus V infinity squared. Okay, that will be the total power generated. It's not only the thrust times the velocity of the free stream. It has to time the kinetic energy, mass flow rate times the kinetic energy. So the propulsive efficiency, we can normally be denoted it as zeta P, can be defined as useful power available divided by the total power generated. And this will be equation number 5. We then substitute equation 3 as well as equation 4 into the new equation 5. Then we have expression number 6. Okay, so substituting the thrust equation which is equation 1, right, into this equation number 6, we then have the element of only this. We substitute T equal to Vj minus V infinity. M dot Vj minus V infinity. So we will substitute J T here, which is coming from equation 1 into equation 6. Then we have equation number 7. So now we want to divide the numerator and denominator by this element. M dot times Vj minus V infinity times V infinity. Okay, then it can be simplified. Equation 7 can be simplified to become this expression. The zeta P propulsive power equal to 2 over 1 plus Vj over V infinity. That will be the equation number 8. So try your very best to derive from equation 1 until you come to equation number 8, which is the simplified version of the propulsive power. The nature of the trade-off between thrust and efficiency is now clearly be seen by examining equation 1, the simplified thrust equation, with equation 8, which is the zeta P. So from equation 8, maximum 100% propulsive efficiency is obtained when the jet velocity equal to the free stream velocity. In this case, zeta P will be 1. Okay? So in this particular case, when the propulsion device hurtles through the laboratory at the velocity V infinity into the stationary air ahead of it, and the air is exhausted from the device with a velocity Vj relative to the device, which is equal to the velocity of the device itself. In this case, zeta v equal to 1, where Vj equal to V infinity, then relative to the laboratory, the air simply appears to pop out of the back end of the device with no velocity. So you will experience no pulse from the vehicle. Okay? So in other words, so since the air behind the device is not moving in the laboratory, then there will be no wasted kinetic energy. Okay, on the other hand, if Vj equal to V infinity, we know that there will be no thrust. Equation 1 will become 0. Hence, is this compromise, we can achieve a maximum propulsive efficiency of 100%, but with no thrust. A self-defeating situation. So you will not have a thrust because Vj minus equal to V infinity. In the thrust equation, you will get no thrust. So in this compromise, we can find the reasons for the existence of various propulsion devices listed earlier, right? Which we have four just now: the propeller, turbojet, turbofan, as well as the turboprop. Okay, a propeller with its relatively large diameter processes a large mass of air, but gives the air only a small increase in velocity. Considering equation 1, T equal to m times the velocity difference, a propeller produces thrust by means of a large mass with a small change in velocity. And therefore, considering equation 8, we will have a high propulsive efficiency. Okay? I hope it makes sense. So the propeller is inherently the most efficient of the common propulsive devices, because you only need a small change in velocity with the movement of very large mass. You will get a high propulsive efficiency. However, the thrust of the propeller is limited by the propeller tip speed, because you cannot turn the propeller higher than the propeller tip speed. Not you will be damaged. So if the tip speed is near or greater than the speed of sound, what happens is that shock wave will form on the propeller. This is not good for propeller. So this greatly increases the drag. When that happens, the drag on the propeller will increases, which increases the torque on the reciprocating engine, which then reduces the rotational speed of the engine, which then eventually reduces the power obtained from the engine itself, and which is manifested in a dramatic reduction of thrust. So instead of getting more thrust, you will get less thrust. So in addition, what will happen next is that the shock wave reduce the lift coefficient of the affected airfoil sections, making up the propeller, which then further decreases the thrust. There is a limit, and the rotation of the propeller has a limit. So the net effect is that at high speeds, the propeller becomes ineffective as a good thrust producing device. This is why there are no propeller driven in transonic or supersonic airplane. Okay, that's one of the reasons that it is not suitable for a very high speed airplane. In contrast to a propeller, you know that the gas turbine engine produces its thrust by giving a comparably smaller mass of air a much larger increase in velocity. So this is the opposite of the propeller. Okay? Reflecting on equation 1, the thrust equation, we see that the mass may be smaller than that for a propeller, but the velocity difference is much larger. Hence, jet engine can produce enough thrust to propel airplane to transonic and supersonic flight velocity by having a low mass flow but higher velocity effect. Because DJ, jet velocity, is very much larger than the free stream velocity. From equation 8, the propulsive efficiency will be very less than for a propeller. Because of the trade-off between the thrust and efficiencies discussed above, in modern aeronautics, we see low speed airplanes powered by the reciprocating engine or propeller combination because of the increased propulsive efficiency. And we see high speed airplanes powered by jet engines because they can produce ample thrust to propel aircraft to transonic and supersonic speed. We also see a reason for a turbofan engine, a large multi-blade fan driven by a turbojet core, which is designed to generate the thrust of a jet engine, but with an efficiency that is more effective of propellers. And even more, that combination of a propeller driven by gas turbine engine, such as the turboprop, which has a nice niche with airplanes in the 300 to 400 miles per hour range. Okay. In summary, the purpose of this section, thrust and efficiency, the trade-off, has been to give you an overall understanding of the fundamental trade-off associated with different flight propulsion devices. So this understanding is helpful for studies of airplane performance and discussion about airplane design. So in the subsequent section, which we are going to look right after the break, we will briefly examine those aspects of each class of propulsive device, which are directly relevant to our considerations of airplane performance and design. So I believe it is good to stop here so that we can look into the topic on reciprocating engine, propeller combination. We will then touch upon the variation of thrust as well as the specific fuel consumption, velocity and altitude that will affect the performance of the engine. Then we touch upon the propeller. Okay, so I believe we can have a short break so that we have a good time to discuss right after the break the section on 8.3. Right? So before we had our short break, just now we have already looked into the overview and thrust efficiency trade-off. Okay, so now next we will look into the reciprocating engine propeller combination. We look into the variation of thrust and specific fuel consumption, velocity and altitude right after that. The basic operation of a 4-stroke spark ignition engine, we have already looked into a detailed explanation in our earlier topic on piston engine. Okay, this is just a recap of what's going on, which is illustrated in figure 8.3. Okay, this illustration given a piston cylinder arrangement where the translating up and down movement of the piston is converted to rotary motion of the crankshaft via a connecting rod. Okay, so this particular diagram, figure 8.3, shows the diagram of 4-stroke Otto cycle for internal combustion spark ignition engines. Right? So on the intake stroke, the intake valve is open. Okay, and the piston move down, intake valve open, the piston move down, and then fresh fuel and mixture is sucked into the cylinder. Okay, and during the compression stroke, so where the piston moves upwards, where it compresses the mixture of fuel and air, the valve are then closed. This particular valve is closed. If you look here, it is open. It is in the position of open. Now the valve over there is already closed, and the gas in the cylinder is compressed to a higher pressure and temperature. So combustion is initiated approximately at the top of the compression stroke as the first approximation. And the combustion is rapid and is relatively complete before the piston has a chance to move very far. Hence, the combustion is assumed to take place at constant volume. So during the combustion, the pressure increases markedly, and this high pressure on the face of the piston drive the piston back down. Right? When combustion occurs, it drives the piston backs down, going down back. And this is the main source of the power of the engine. So finally, the exhaust valve open back, and the piston move up on the exhaust stroke, pushing most of the burnt fuel air mixture out of the cylinder. Then the four-stroke cycle is repeated, and the same goes back to step number 1. On what characteristics of the engine does this power depend? Right, so this will be answered rest on the 3 primary features as follows. And the first one is that there is a shear size of the engine, as described by the displacement on its travel from the top of the stroke to top dead center (TDC) to the bottom of the stroke, bottom dead center (BDC). The piston sweeps out a given volume and called the displacement of the cylinder. The total displacement of the engine is that for a cylinder multiplied by the number of cylinders. And we denote the displacement by D, small d over there. The larger the displacement, the larger the engine power output, and everything else being the same. The second aspect is that the number of times the piston moves through its four-stroke cycle per unit time will eventually influence the power output. The more power strokes per minute, the greater the power output of the engine. If we look carefully in figure A3, we note that shaft makes 2 revolutions for each four-stroke cycle. So clearly, the more revolutions per minute, the more power it will be generated. Okay? The power output of the engine is directly proportional to the revolution per minute RPM. The third aspect is that the amount of force applied by the burnt gas on the face of the piston after combustion will affect the work performed during each power stroke. As the higher the pressure in the cylinder during the power stroke, the larger will be the power output. And average pressure, which is indicative of the pressure level in the cylinder, is defined as the PE. What is PE? It is the mean effective pressure, and therefore we can state that the power output from the engine to the crankshaft or the shaft brake power P is proportional to the change in the mean effective pressure. The D times PE, mean effective pressure, times the revolution per minute. That should be your equation number 9. This figure shows the typical internal combustion reciprocating engine. It has strong life forming T10 5 TJ10 540, a turbocharged piston engine. And that shows the same principle as what we have already discussed earlier. If we look here, the specific fuel consumption, which is a technical figure. SFC is a technical figure of merit for an engine. Normally when you want to choose an engine, you want to know what is the specific fuel consumption of the engine and how efficiently the engine is burning fuel and converting it to power. Right? For an internal combustion reciprocating engine, the SFC, okay, is use the symbol small c over here. And C is the weight of fuel burned per unit power per unit time, or equal to the weight of fuel consumed for a given time increment divided by the power output time in time increment. Hence, C can be expressed in terms of the unit here. It can be in terms of pound per feet, pound per second times second, or Newton per watt second. Okay, but normally we are being used to use the symbol SFC. However, over the years, conventional engineering practice has quoted the specific consumption in the inconsistent units of pound per horsepower per hour. Okay, so these are the units you will find more specification for internal combustion reciprocating engine. To emphasize this difference, we will denote the specific fuel consumption in this inconsistent unit by the symbol SFC. Right? Pound per horsepower hour. Let us look into the variation of thrust, specific fuel consumption, velocity, and altitude with respect to the engine efficiency. Okay, in this aspect, we propeller. So, if we look back in equation 9 just now, right, the P is the power that comes from the engine shaft, and it is sometimes called the shaft power. Consider the engine mounted on an airplane. As the airplane velocity V infinity is changed, the only variable affected equation 9 is the pressure of the air entering the engine manifold. And due to the stagnation of the airflow, in the sometimes we call it as the ramp effect. In effect, as the free stream velocity increases, the ramp pressure will also increase. It is reflected as an increase in the PE, mean effective pressure, which is shown in equation 9, which in turn increases the shaft power via equation 9. So for the high velocity propeller driven fighter airplane, in the case of World War II, this effect had some significance. However, today, reciprocating engines are used only on low speed general aviation aircraft, and the ramp effect can also be ignored. So we assume the shaft power P is reasonably constant with the free-stream velocity V infinity. Okay? So for the same reason, the specific fuel consumption SFC is also assumed to be independent of the free-stream velocity. In the US, physical manufacturers of aircraft propulsion engines are 39 centimeters, and Electron, like the one that we see in Figure 8.4 just now, the horsepower rating at sea level for these type of engine generally range from 75 to 300 horsepower. For this engine, a typical value of the specific fuel consumption is of 0.4 pound of fuel consumed per horsepower per hour. So as the airplane's altitude changes, what happens when the airplane at the sea level moves to 10,000 feet, 20,000 feet, 13,000 feet? So the engine power will also change. So this is easily seen in equation 9, because it is the factor of altitude. And the air pressure, known as also the air density, decreases with an increase in altitude. So which in turn reduces the PE, mean effective pressure, PE in relation 9, which directly reduces the shaft power because it is directly proportional. And the variation of the shaft power with altitude is usually given as a function of the local air density. Right? So to a first approximation, we assume the shaft power P over the P naught equal to the density over the density naught and P and the rho are the shaft power output and the density, respectively at the given altitude, as well as now P naught and then rho naught are the corresponding values at the sea level. There is also a temperature effect on the mean effective pressure PE in equation 9. An empirical correlation given for the altitude variation is taken from Thornback. Variation of the shaft power P. Right. So this is a correlation again. And the specific fuel consumption SFC is now relatively insensitive to the changes in altitude, at least for the altitude range for general aviation. So we assume the specific fuel consumption is constant with altitude. Now, the next part is the propeller, 8.3.2. If you look in the history, Bill Murray in 1902 was the first person to recognize that propeller is essentially a twisted wing. We have already looked in detail in terms of the propeller theory. So this is just again to look at the effect of other factors in terms of the performance of a propeller, which is a twisted wing oriented vertically to the longitudinal axis of the airplane. And then the forward thrust generated by the propeller is essentially analogous to the aerodynamic generated on the wing. And like a wing, the propeller also produces friction drag. It also produces form drag. It induces drag as well as the wave drag. A rotating propeller the same drag, such like the wing set. So this propeller drag is a loss mechanism because it is a drag, and that is, it basically robs the propeller of some useful power because the existence of drag. So this power loss means that the net power output of the engine or the propeller combination is always less than the shaft power transmitted to the propeller through the engine shaft. Hence, the power available PA from the engine or propeller combination is always less than the P, the shaft power. So this is illustrated schematically in the following figure, 8.5, and the propeller efficiency zeta PR is defined as the available power PA equal to the zeta PR propeller efficiency times the shaft power output from the engine. Where in this case, the propeller efficiency zeta PR is less than 1. If you look at the figure 8.5 over here, shows the schematic illustrating shaft power P coming from the engine that turn the propeller, provided the power available by the propeller PA. PA is always less than P, where PA is equal to the zeta PR times P. Alright? So the propeller efficiency, zeta PR, is a function of the advance ratio. We have an advance ratio, J, which is equal to the free stream velocity V infinity, the number of propeller per revolution per second, N, and D is the propeller length. Alright? So this will make sense when you examine the local airflow velocity relative to the given cross-section of the propeller as sketched in figure 8.6. This is a figure 8.6. We have velocity and relative mean direct for a section of a propeller, a revolving propeller, for in case A for low free spin velocity and case B for high free spin velocity. You can see there is an alpha there, there is a beta there. Looking at the difference between the two, we will explain in terms of the cases. And you can see that the leaf generated also in a different direction for the two different cases of free spin velocity. Here, the local relative mean is the sector vector sum of V and the translational motion of the propeller airfoil section due to the propeller rotation, namely R omega, where R is the radial distance of the airfoil section from the hub, propeller hub, and omega is the angular velocity of the propeller. So the angle between the airfoil chord line and the plane node of rotation is the pitch angle beta. The angle of attack alpha, this is alpha actually, is the angle between the chord line and the local relative mean. So the angle of attack alpha clearly depends on the relative values of free spin velocity and radial distance times the angular velocity omega. If we look at figure 8.6a for the case of low velocity receipt, the alpha is large positive value, so it is on the positive side, okay, large positive value, producing an aerodynamic lift acting in the general thrust direction. Whereas in figure 8.6b, the value of free spin has greatly increased. All other parameters are the same. And here, in 8.6b, the relative mean has moved to the other side of the airfoil section, giving rise to a negative alpha. You can see the alpha is now negative value instead of a positive value from the chord line. Okay? As well as the aerodynamic lift force L pointing in the opposite direction of the positive thrust. So you can see that the lift generated are also in the opposite direction. Okay? In conclusion, the local angle of attack and hence the thrust generated by the propeller depends critically on the free spin velocity, right? Whether the free spin velocity is high or low, as well as the radial distance and the angular velocity. Note that the R omega is evaluated at the propeller tip, which is the diameter of 2 times 2 pi n, where in this case the R omega at the tip equal to the pi times 10 times the d, and hence the ratio of the free spin velocity over R omega, which sets the direction of the local relative mean, is given by the expression equation 14 over here. So when we evaluate the propeller in equation 14, which gives this expression in terms of the advance ratio. Okay? You can see from here, equation 15, the advance ratio, which is a dimensionless quantity, plays a strong role in propeller performance. Indeed, dimensional analysis show that the J, the advance ratio, is a similarity parameter for propeller performance, in the same category as Mach number and Reynolds number. Hence, we should intuitively feel comfortable with the opening statement of this paragraph. Propeller efficiencies is indeed a function of the advance ratio G. A typical variation of the efficiency of the propeller, zeta PR with advanced ratio, is given in figure 8.7. This data obtained from experimental measurements of Hartmann and Biermann for a NACA propeller with a clockwise air force section and 3 blades. 7 separate propeller efficiency curves are shown in figure 8.7, will be shown in the next slide. Each one for a different propeller pitch angle beta. Measured at a station 75% of the blade length from the propeller arm. Examining this figure, we can see clearly that the efficiency of the propeller for a given pitch angle beta is 0 at advanced ratio equal to 0, increases as advanced ratio increases, goes to a maximum value at some value of J, and then goes to 0 back at some value of IAJ. So you can see here, zeta PR, what I mentioned just now, it grows to the maximum and then goes back to 0. Okay? For different set of blade angle. Let us examine why the propeller efficiency curve has this shape. First, the reason why efficiency of the propeller equal to 0 and advanced ratio equal to 0. Okay. We can see from equation 3 and equation 13 and consider an airplane at 0 velocity, standing motionless on the ground with the engine running, producing thrust. This is called the static thrust. From equation 3, the available power equal to 0 when V pre-stream velocity equal to 0. No power produced at 0 velocity, even though the propulsive mechanism is generating thrust. Right? So, when equation 13 is applied, in this case, the available power equal to 0, but the sharp power is finite, where sharp power P is the sharp power coming from the internal combustion reciprocating engine, and is not a direct function of the pre-stream velocity. Hence, for pre-stream velocity equal to 0, equation 13, if you recall that equation 13 dictates that efficiency of the propeller is also equal to 0. And also, when pre-stream velocity equal to 0, then the advanced ratio G is also equal to 0. This is why at zeta PR, efficiency of the propeller equal to 0 and advanced ratio equal to 0 for all curves shown in figure 8.7 over here. Okay? So the shape of the propeller efficiency curve as the advanced ratio J is increased above 0 is explained as follows. For clarity, the variation of zeta PR, propulsive efficiency for the propeller with J advanced ratio for a given pitch propeller is sketched generally in 8.8A. Okay, so we have station 1, 2, 3, 4, 5 over here. Then we are going to explain one by one. Also, the variation of the lift to drag ratio for a given propeller airfoil cross section versus angle of attack is then sketched in 8.8B. This is L over D, lift to drag ratio with the angle of attack alpha. Okay, so we will discuss the phenomena and keeping in mind the geometry shown in figure 8.6 earlier. So, in a given situation, a fixed pitch propeller beta for a given propeller cross section is fixed, and keep in mind that a propeller blade is twisted. Hence, the beta is different for each cross section because it is twisted. Right? So the pitch angle will be different. A fixed pitch propeller is one where the value of beta at any given cross section is essentially locked in mechanically. We have already explained this when we talk about the propeller blade theory, where the pilot cannot change the beta angle during flight because it is locked. Examine figure 8.6 for a given number of propeller N, the R omega is constant, however the airplane changes its velocity, V infinity will change, and consequently the angle of attack alpha will also change as shown in figure 8.6 earlier. At the position of V infinity equal to 0, the angle of attack alpha is the same as the angle between the propeller effort hotline and the plane of rotation. And that is the angle of attack is also the pitch angle, and for this case only, and where V infinity of free stream equal to 0. For a pitch angle of say 30 degree, pitch angle 30 degree, okay, the angle of attack is also 30 degree. For this case, the airfoil section most likely would be stopped. Right? So this situation is labeled in figure point 88A and B by point number 1. So this is point number 1, where efficiency of propeller equal to 0. Right? And the advance ratio is also equal to 0, where V infinity is equal to 0. So the angle of attack is large. This is indicated in figure 8.8b, where angle of attack is large. Alpha is the largest in this case at 0.1, right? But the lift to drag ratio is not that high. Okay, so it is down here. And then returning to figure 8.6, we imagine that when the free stream velocity is increased, keeping n constant, this gives us point number 2, illustrated in figure 8.8. Okay, point number 2 over here is this situation. Okay, and then we can note that L over D is also increased. So you can see L over D is also increase over there at station number 2. The given airfoil section is now operating with an improved aerodynamic efficiency. Let us continue to increase the free stream velocity, say to a value that the angle of attack corresponds to the peak value of L over D as shown in figure 3 in 8.8b. As shown here, we have the angle of attack alpha, which provided L over D equal to at the highest peak over there, and we can see here the maximum propeller efficiency is also at maximum. Okay, we have the J advance ratio is already more than mid value. So what happens is that if all the other propeller airfoil cross sections are designed to simultaneously correspond to the point where L over D is max, then the net efficiency of the propeller will be maximum. Okay, as soon as point 3. That's now. Let us continue to increase, increase the V infinity, keeping everything else the same. The angle of attack will continue to decrease, say to 0.4. However, this corresponds to a very low value of L over D, and result in a poor propeller efficiency as indicated by 0.4. You can see here, if you reduce, you can get L over D very low, and alpha to be also very low. High alpha, low alpha also can provide L over D at the lowest. Okay? If we still increase V infinity, the local relative will eventually flip over to a direction below the airfoil line. Right? So that's what happened when we 8.8b. Remember the direction of the lift is also already flipped. This is what happened. And the direction of the local lift vector will flip also, acting in the negative plus direction. When this happens, the propeller efficiency is totally destroyed in this particular figure. So it's already, there's no lift generated, right? In summary, we already explained why the curve zeta PR versus J first increases as J is increased, then peaks at the value of the maximum zeta PR, and then finally decreases abruptly. And this is why propeller efficiency curve, as shown in figure 8.7 and 8.8a, look the way they do. And it is like that, and you can continue. So for fixed pitch propeller, which were used exclusively on all airplanes until the early 1930s, the maximum propeller efficiency is achieved at a specific value of J, hence also specific value of V infinity. Okay? So this value of J was considered the design point of the propeller. So advanced ratio are used to put a limit in terms of the design point of the propeller and could correspond to the cruise velocity or velocity for maximum rate of climb or whatever condition the airplane designers consider most important. However, whenever the free stream velocity was different from the design speed, zeta PR decreased precipitously as reflected in figure 8.8a. The off-design performance of a fixed-pitch propeller caused a degradation of the overall airplane performance that became unacceptable to airplane designers in the 1930s. Right? However, the solution to this problem is contained in the data shown in figure 8.7, where we see the maximum of propeller efficiency for different pitch angles occurs at different values of advanced ratio J. Indeed, for the propeller data shown in figure 8.7, the locus of the points for maximum zeta PR forms a relatively flat angle over a large range of J value. Hence, the free stream value at a value of approximately the maximum propeller efficiency, which is equal to 0.85. Clearly, if the pitch of the propeller could be changed and the pilot during flight so as to ride along this flight angle, then high propeller efficiency could be achieved over a wide range of free stream velocity. So, basically, if the mechanism of the propeller pitch could be altered, right? So the pilot can control the pitch angle, then they can have a high propeller efficiency over a wide range of free stream velocity. So thus the variable pitch propeller was born. Okay, that's where this type of variable pitch propeller was initiated. The entire propeller deck is rotated by a mechanical mechanism located in the propeller hub, and the degree of rotation is controlled by the pilot during flight. And the improvement of design propeller performance brought about by the variable pitch propeller was so compelling that this design feature is ranked as one of the major aeronautical technical advances in the 1930s. However, the variable pitch propeller, we can see that was not the final answer to the propeller design during the era of the mature propeller-driven aircraft. Rather, an improvisation called the constant speed propeller eventually supplanted the variable pitch propeller in most high-performance propeller-driven aircraft. To understand the technical merit of a constant speed propeller, you can return to equation 13, and power available from reciprocating engine propeller combination depends not only on the propeller efficiency zeta PR, but also on the shaft power coming from the propeller engine. In turn, the shaft power P is directly proportional to the rotational speed RPM of the engine as shown in equation 9, For an airplane, the load on the shaft of the piston engine comes from the aerodynamic torque created on the propeller. So this torque is generated by the component of aerodynamic force exerted on the propeller in the plane of rotation. And acting through a moment arm to the shaft, and this aerodynamic component is a resistance force, tending to retard the rotation of the propeller. So in the case of variable pitch propeller, the pilot change the pitch angle, the torque change, which in turn cause a change in the engine RPM away from the optimum value of the engine operation. So this was partially self-defeating. In the quest to obtain, we want higher zeta PR by varying the propeller pitch. The engine power P was frequently degraded by the resulting change in RPM. Thus, constant speed propeller was born, and constant speed propeller is a variant of the variable pitch propeller, wherein the pitch of the propeller is automatically varied by a governor mechanism to maintain a constant RPM for the engine. Although the constant speed propeller is not always operating at maximum efficiency, so the product of zeta PR, efficiency of the propeller, times the shaft power in equation 13 can now be optimized. Also, the automatic feature of the constant speed propeller frees the pilot to concentrate on other things, something especially important in combat. The use of variable pitch and constant speed propellers greatly enhances the rate of climb for airplane compared to that for a fixed pitch propeller. So this kind of advantage illustrated in figure 8.9. Figure 8.9 is shown as much for historical value as for technical amplification. It shows clearly how much the advantage of a constant speed propeller was appreciated by time. So in this particular figure, the altitude versus horizontal distance climb path of a representative airplane is shown for 3 different propeller fixed pitch, 2-position controllable, kind of variable pitch propeller with only 2 settings as well as the constant speed. So you can see here altitude versus distance comparison of airplane climb performance for 3 types of propeller. We have the constant speed propeller, 2-position control propeller, and fixed pitch propeller. So you can see here for fixed pitch propeller, it can go very far, okay, compared to compared to 2-position control propeller and constant speed propeller, which can climb altitude very fast compared to the other type of propeller control. Right? So you can see here the difference between the 3 types of different propeller types. So the tick marks in various points, you can see here 2, 4, 6, 8, and so on. Okay, give the time required for takeoff to reach that point. Clearly, you can see that constant speed propeller here, which it requires a short distance to reach to a certain altitude. Okay, right. So you can see here it reaches a given altitude in less time and over a shorter horizontal distance, which is a characteristic particularly important for the high performance airplane that characterizes the era of mature propeller-driven airplane. Finally, we note another advantage of being able to vary the propeller pitch, namely feathering the propeller. The propeller is feathered when its pitch is adjusted, so you can adjust the pitch angle of the propeller itself so that the these minimize, and there is little or tendency for auto-rotation when the engine is turned off, but the airplane is still. The problem is present when an engine failure occurs in flight, and sometimes when the multi-engine airplane is taxiing on the ground with one or more engines being turned off. Okay, so basically we have already covered for the last 15 minutes to look into the reciprocating engine propeller combination, and earlier before the break we looked at the overview and thrust efficiency, the trade-off for today's session, and we shall continue next Monday and to look at the last topic on chapter 8, and we will look into turbojet, turbofan and turboprop, how these kind of engine can be affected in terms of the propulsion system characteristic, and finally look into the afterburning and more specific fuel consumption. That will be done next Monday in our lecture number 15. Okay, thank you very much for your attention. I look forward to meet you again in our final lecture next week. Hope that we can complete our syllabus for this course. So with that, thank you very much, Dr. An and students.